Hello everybody, my name is David Blum and I'm happy to be presenting on behalf of my co-authors our paper entitled The Development and Verification of Control Sequences for Single Zone Variable Air Volume Systems based on ASHRAE Guideline 36. What I'll do today is start out with some background on what Single Zone Variable Air Volume System is, as well as what ASHRAE Guideline 36 is. And then I'll talk about how we implemented the control sequences based on ASHRAE Guideline 36 in what's known as the control description language, which I'll also introduce as part of the background. And then I'll talk about a case study that's used to verify the performance of these sequences, as well as compare them against more conventional sequences we've seen in the past. And I'll conclude with a summary of our main findings and some thoughts on future work. I'll start out by describing a single zone VAV system. This is a heating, ventilating, and air conditioning system that's often used to serve medium to large single floor spaces such as small retail stores, classrooms, and auditoriums. It's really made up of a single air handling unit that has a number of pieces of equipment in it, the first being a supply fan, and then also a heating coil and a cooling coil. And then on the left there, you see a number of dampers that are used to determine how much of the return air is recirculated and combined with outside air and then sent through the system again to provide heating or cooling, and how much of it is exhausted to the outside. Now that outside air being brought in serves two purposes. First, to provide minimum ventilation air required to maintain the indoor air quality of the space. And the second being, if the outside air is cool enough, using it for cooling so that we don't have to turn on the cooling coil and utilize that energy. ASHRAE Guideline 36 is a standard that was published by the American Society of Heating, Refrigerating, and Air Conditioning Engineers in 2018. That's really meant to propose a standard set of best-in-class sequences, control sequences for the operation of both single and multi-zone VAV systems. Here in this project, or in this paper, we're only looking at single-zone systems. And really the purpose, or there's two main purposes of this standard. First, it's to reduce energy consumption in a large number of buildings, as well as improve the indoor environment, both in terms of thermal environment and indoor air quality. And the second is by publishing these standard sequences to help reduce the time for engineering, specification, programming, and commissioning processes that the industry sees in developing and implementing sequences. And lastly, the control description language, or CDL, was developed as part of the Open Building Control Project, which is a project that generally looks at streamlining the process of developing, testing, implementing, and commissioning building control sequences. And CDL is a subset of Modelica with its own data types and elementary blocks, and it can really be used to specify control sequences in computer code that can be used for both explicit simulations, say in a Modelica model, as well as translated into a building automation system and used in real buildings. So the objective of this paper is really to focus on the single zone sequences and how we've implemented them in CDL, tested them on a simple case study, and compared their performance to more conventional sequences we've seen in the past. There is a previous paper published in 2018 that's referenced on the bottom there that focused on the multi-zone sequences and implementing them in CDL and showing their performance in a closed-loop simulation. But here we focus on the single-zone sequences. So in terms of the actual sequence implementation, I'll start out with some general information. The sequences are implemented as Modelica packages within the Modelica Buildings library, and they're implemented in a modular way based on subsequences so that the final controller can be more customizable as allowed by ASHRAE Guideline 36. There's documentation provided throughout through the use of the HTML info section. There's hysteresis and timer blocks used to control for numerical or sensor noise or equipment chattering. And there's verification models included with each subsequence to show users how the sequences are used and their performance, as well as used for unit tests for code maintenance. So I just want to go over a couple of the, or really three, of the core sequences that have been implemented here, just to give you an idea of what the intent is, but then also how we've sort of implemented them in CDL. So the first one is set points for supplier temperature and fan speed, and these are really coordinated based on the amount of heating and cooling that's needed in the space, and that's basically represented by heating loop signal that you see on the lower left, and then a cooling loop signal that you see in that plot in the lower right. And so in the heating case, as more heating is needed, first the supplier temperature is increased, and then if even more heating is needed, the supply fan speed is increased to provide more air to the space. And in the cooling case, it's a little bit more complicated, but basically what this sequence is doing is staging on the economizer first, using the economizer as much as possible by increasing the fan speed if the difference between the outside air temperature and inside air temperature is really great. And basically, again, using this outside air as much as possible before turning on the cooling coil. And you can see on the right there the implementation in the CDL blocks. And if I just show some verification here, we see in the upper right for a couple different scenarios of inside and outside air temperatures, plotting the cooling loop signal on the x-axis and the fan speed on the y-axis, we see that the sequence implementation is able to reproduce the sequence intent that you see on the left. And on the bottom right, we see something similar where if we plot the cooling coil supplier temperature set point as well as the heating / economizer supplier temperature set point as a function of cooling loop signal, then again we see we are able to reproduce the intent of the sequence that you see on the left. The next sequence is economizer control, and here there's two significant parts to point out. The first is basically determining what the minimum and maximum limits are for the outside air damper position to make sure that at any fan speed or as fan speed changes, we're able to maintain our minimum outside air requirements. And so that's being done on the top left. And then the bottom left, we see a sequence or a subsequence that is using those limits and then also using how much heating or cooling is needed in terms of supplier temperature set point to modulate the outside air damper, the return air damper, and also the heating coil in coordination. And we see that implementation in CDL on the right. And we see a verification where on the top right, we kind of see the scenario here that we have a constant heating / economizer set point temperature, and the measured supplier temperature is increasing from 16 to 20 over time, and we then see the corresponding signal, supplier temperature control signal dropping from 1 to 0. And if we plot then outside air damper position, return air damper position, and heating coil as a function of that supplier temperature control signal, we see we're able to reproduce the intent of the sequence that we see on the left. The final sequence that I just want to point out is the minimum calculation of that minimum outside airflow requirement, which in Guideline 36 is based on ASHRAE Guideline 62.1. That basically takes into account how many people are in the space, what the area of the space is, and what's known as the air distribution effectiveness, which essentially is whether or not it's in heating or cooling mode, to determine how much outside air is needed to properly ventilate the space. And on the right, we see a scenario on the top where our number of occupants in the space is increasing from 0 to 4. In the middle, we see that the zone air temperature is increasing a little bit more slowly, or I'm sorry, a little faster than the discharge or supply air temperature. And so there the system is basically shifting from heating to cooling mode. And on the bottom, we see the minimum outside airflow that's calculated, also increasing with the number of occupants, and then there's a step change there when the air distribution effectiveness changes from essentially heating mode to cooling mode. So moving on to the case study, we implemented a system model with the physical components modeled using components from the Modelica Buildings library, and we basically have a single room model that's based on best test construction, and then we have our air handling unit model in the middle there, and then our controller model, which is again implemented using our CDL implementation. And then there's a number of other ancillary components here to supply weather data and other types of information. Our baseline controller uses the same exact room and system model, except that we switch out the controller for a baseline controller. And that baseline controller uses what's known as single maximum airflow control. And really, it's a much simpler type of controller that basically, during cooling, first modulates the fan speed from a maximum down to a minimum that supplies the correct amount of outside air, and does so at a constant supply air temperature, and then for heating keeps that constant supply air flow to maintain minimum outside air, but then stages on the heating coil to provide heating. We also have a Drybulb economizer, which essentially turns the economizer on if the outside air temperature is less than the zone air temperature and can be used for cooling. And the minimum outside air damper position is really set to meet that minimum outside air flow at the minimum fan speed, but it is not reset like it is in the Guideline 36. And so in general, the results are that the Guideline 36 saved approximately 17% yearly energy, and the savings were mainly from cooling energy at the expense of some amount of fan energy. But you can really see in the chart here on savings per month that the cooling energy is really reduced in Guideline 36 versus the baseline. And we can see here on the top plot, well, both plots are zone air temperature. On the top we see for a summer week, and the bottom we see for a winter week, and we see for both systems that the sequences are able to provide adequate thermal comfort here. What I want to point out really is this outside airflow control comparing both systems. So I've only changed out, we're looking again at a week in the summer, and in blue we see the baseline, and in green, dark green, we see the Guideline 36. And two things to point out. The first is we can see that Guideline 36 does a better job of keeping the outside airflow to the correct minimum, so that it's not overventilating the space and introducing additional energy needed to cool that outside air. We see that, say, on day July 29th. But then, say, on August 1st, we see that in the afternoon, when actually the outside air temperature drops a lot, we see that outside airflow increase a lot more in Guideline 36 than we do in the baseline. And this is basically showing that the guideline is able to significantly improve the ability to bring in more outside air in this condition, and therefore save a lot of energy. So in summary, ASHRAE Guideline 36 sequences were developed to save energy and also implementation costs for both multi and single zone VAV systems. In this paper, we implemented those single zone sequences in CDL and tested them in a closed loop case study using a Modelica simulation model. And we found for this specific test case that we saved about 17% energy over a conventional controller, really due to the improved utilization of economizer free cooling. So these sequences and models are available in the Modelica Buildings library, and future work really entails testing in additional climates, testing against additional control baselines, and continued code maintenance in the Modelica Buildings library. So I just want to acknowledge our support by the Department of Energy, Building Technologies Office, as well as the California Energy Commission, and specifically really Taylor Engineering, who's providing funding for this work as a subcontract in the EPIC program. So thank you for your attention, and I'm happy to take any questions either in our real-time session or feel free to shoot me an email that you see on the screen there. Thanks.